So Nicolai sounds a little bit familiar here in this room. Usually people name me Nico, and that's it, unless I made something wrong, which I did. I'm involved in C++ standardization for more than 20 years. And so you can always come to me and say, it's your fault. Yes, it's my fault. And I've documented this fault in a couple of books. So you might have seen one of them or two. And they all have significant errors. So whenever you read an error, please send me an email. If I'm a little bit confusing and if I get slower and slower, the reason is the following. Last week we standardized, we made feature freeze of C++20. And that was at the exact opposite side of the world, in Kona, Hawaii. So it's a 12-hour time zone difference. So it's the other side of the world. For me, it's now 1:30 a.m. So if I fall asleep, please shout out loud. Might happen the first time in a talk this way. So let's talk about C++17, which is out now for 2 years. And we thought, well, it's just a few nice features, but is there more? Is there something significant, or is there something I should know? Well, the next hour is dedicated to the try that you may learn something about C++17. Who has used C++17 already? Okay, good. So, and of course, with each and every program, we have to start with initialization. So, how do we initialize? That's an interesting question in C++. We started from C with the way, just looking at ints, having no initialized value and initialization with an equal sign. Then we added with the old C++, the usage of parentheses. And then in C++11, we introduced curly braces. Now the whole community is confused. What should I use to initialize an int? And by the way, that's not all. I think there are 19 different ways to initialize an int now. So let's talk a little bit about it, because I think you might still not use the right way to initialize an object, and because I use it in the slides. Let's first talk about parentheses. Are parentheses a good way to initialize an object? Well, this is a proof that it's not, because this is not initializing an int, it's declaring a function. And of course, you know what this does. Do you know? Is this valid C++? Who thinks this is valid C++? I10. It depends? Well, depends is always a good answer in C++, yeah. So this is a compile time error. Jason, I'm sorry. So, but if you put an equal sign in between, what that? That's fine. Let's initialize an int with 9 because this is the comma operator. We all know that. And if I put an equal sign again and put int before, what's that? Compile time error. Yes, we all know these rules, huh? Don't we? No, we hate them. And therefore, please don't initialize with parentheses anymore. Don't do it. There's a better way. Use curly braces. Well, except that we made a mistake in C++11. C++ is a software project. This software project is 45 years old. It started 45 years ago under the name of C. And we are still backward compatible. Please take that in mind. We make mistakes, and the mistakes are not done by a chief architect. They are done by us. No, not by us, me, and some other guys. It's you. This is a community-driven standard. And that means whenever you come to me and complain, I will tell you it's your fault, because you haven't been there. I'm serious about that, a little bit, of course, because that means, yes, we make mistakes, we go into different directions, and sometimes if you think about some inconsistencies, we have no chief architect. We just have 150 chief architects right now, or even more. So please take that into account. And for that, it's not too bad what we made. So yeah, we had invented different ways of initialization. One was called uniform initialization with curly braces. And I think it's a good thing until we looked at using auto. Because when we used auto with an equal sign, everything was fine. This initialized I9 as an int with the value 42. But when we use curly braces, and I just told you use curly braces, this was a problem. Because we made a mistake in C++11. And the mistake was this did not initialize an int. This did initialize an initializer list of int. So this is a list of ints with one value. Obvious, huh? This was a mistake. And a mistake just combining two new brand features, curly braces and auto. And that's one of the most important things to learn. It's not about new features. And you will see at the rest of this talk, I'm not talking about new features. It's a combination of new features that matters. And that makes things interesting and sometimes weird. So this is fixed. Yeah, we fixed that. Officially, by the way, in C++17 as a defect, that means even in older C++ versions, this is now fixed. And this initializes, in fact, an int with 42. And you can see here in the major compilers from which version on this is fixed, even in C++11 mode. So don't use an older compiler. Yeah, I know this is a wish, but yeah. So, of course, that raises the question, should I use an equal sign there? And the answer is no. This still initializes an initializer list of int. What? What? An equal sign changes the type of an object? Okay. It's just to confuse the Chinese, sometimes people say. Okay. Let's see. We make compromises. This is a compromise of those who like the old way and those who thought the old way was crap. So this is one of the worst decisions we made in C++11. It will probably be fixed in C++20 or 23. Let's see. But for the moment, this means something else. Don't use an equal sign in initializations. Just as a general rule of thumb. So that means, here's the rule. By default, unless you have a good reason to do otherwise, sometimes this is necessary, use curly braces and use no equal sign. Like here, instead of using initializing I2, and you get a lot of initial intuitive initializations. So whenever you initialize an object with empty curly braces, it's initialized. There's an almost in the header. That was not true for atomics, which will be fixed in C++20, but only formally the compilers do it right anyway. This will detect narrowing. It will find out whether a long unsigned value is initialized by a float or by a signed value, which might cause that some of the value is gone, some part of the value. This will make this initialization self-explanatory. This is creating a vector of int with two elements having the value 8 and 15. Some people argue that this is a proof that uniform initialization is bad because they are used to some crazy API, which is using parentheses on the right and says, I'm creating a vector initialized with 8 objects, all having the value of 15. Yes, we learn in C++ to think, well, crazy. So self-explanatory is something which is a goal, and therefore you should use curly braces here. We might suddenly see that if we create a hash object and then use it as a function, that there's a difference between the construction and the function call, because we use curly braces here. We might suddenly be able to declare a vector of int that is initialized by all integers read from standard I stream, from the input stream. This will not work with parentheses. A problem I found in the very first book in 1998 with just parentheses, you have to double the parentheses because otherwise this declares a function v. And we have introduced something new in C++17. So you can now initialize enumerations with numeric values just using the uniform initialization, the Braille's initialization. No other way is possible and works. And there's also now support for aggregates that have base classes or base types, and you can use the curly braces even to pass initial values to the base classes. So that's the reason you should use curly braces now. And now let's talk about C++17 from a feature point of view. So the first thing we should look at is the file system library, which we adopted from Boost. And of course, we initialize a path, a file system path, by the command line argument, by the first command line argument, using curly braces. Still works with parentheses. But everything else here is more or less self-explanatory. So we have a regular file, we have a file size, or we can ask for the file size. If it's a directory, we use a directory iterator to iterate over the elements of this directory. And if it exists but is neither a regular file nor a directory, then we do something else. This is more or less taken and as the example from Boost. Who's used Boost file system? Few? Okay. So let's look at this output here in the middle, because we talk about the good things and the scary things of C++17. So let's look in the code in the middle. Let's iterate over a given directory. Guess I give root as a directory. Then you see that we print out that we are iterating over root in quotes, in double quotes. And then while we are iterating, then each path is printed, which is the files in this directory. They are also quoted. And that's the reason is that the output operator here prints out the paths quoted. Which does unfortunately not mean only that double quotes are around it. There's another nice effect. Every backslash is escaped. So if you run this on a Windows machine, you get an interesting output for those who are on the Windows world. Because this is nothing, this is a technical output escaping the backslash by another backslash, but it's not probably something you want to see in a user interface as the output of what is the current path or what are the paths in my directory. We made this as a mistake, and it's too late to fix it. Although we had a beta standard, file system standard, there was not enough attention to find out that this is a significant problem. Now we have standardized it. Now it's too late. Now we have to keep it that way, which means if you want to write portable code from this program, please use .string. So this converts to a string, which does not escape the backslash. And if you still need double quotes around, you have to put it in your code. What else is an issue in this example? Well, it might happen that we ask the operating system 3 times about the nature of a file. Because we first check, is it a regular file? If not, is it a directory? If not, is this a special file? File system operators are pretty expensive. So let's fix that. Here's a way to do that. It's a switch statement. The switch statement initializes the path and then checks the type of the path and then has a case. Different cases for the different types of types I had in the previous section as an if-else chain. So this is a better code. And here's something interesting. Look at the top of the switch there. This is a new switch we introduced with C++17. It's a combination of an initialization and a condition check. It's like in the for loop, you have this first part for an initialization. We have now this initialization also for switch and if. We will see examples with if later on. And that's something you can do now. And the P is valid until the end of the switch statement. So it opens its own scope where this P is initialized. Good. Starting to combine features. Let's talk about something completely different. Not completely different, but a different example. Let's write a function that inserts an element in a vector or some other container, as long as the container supports pushback. So this is a generic code that defines this function. It takes an argument of type t, any type t, and it takes a collection by reference, which is modified because we call collection.pushbackx. Is this a good function? Maybe, maybe not. It's a good example to show you some language features of C++17 and also one library feature, because I want to combine these things. So first of all, I can declare a vector of strings, and I want to insert the string hello here. Does it work? Yes. Now let's insert in this vector an integer, 42. This does not work because the template does not compile, because pushback, it would need that we have a pushback which allows to push back an integer type into a vector of strings, and there's no automatic type conversion for integers to become strings. So what could we do? In the past, we would, for example, be able to say, let's add an override, an overload, let's say. So let's add another function that takes an int and pushes this back by converting the int to a string, where we have the standard function toString since C++11. Does this solve the problem? Next time I want to insert a double, so I need another overload, and you see the problem in general. So in general, we would need two different ways to insert something into this vector, just push back or push back converted to a string, which we can do with some tricky template tricks, but we have something new, which are type traits, which can find out whether t is an arithmetic type. This type trait is already there in C++11, and I could try out if the type I get is an arithmetic type. So if it's an integer or floating point value, let's do the conversion to string before I push back. Otherwise, let's just call push back. Does this code compile? Who thinks this compiles? Raise your hand. Hey, you fall asleep, not me, huh? Who thinks this does not compile? Depends. Here are all keynote speakers. They always say depends. Don't trust them, including me. So, this does not compile. Why? You get some interesting error messages looking like this. This is the error message for the first trial to insert. And the problem is that we have confused something. We have confused runtime features with compile time features. So this is template code, but in the template, we have a check whether type t is arithmetic or not. But once we instantiate this template, all code must be valid. Even the code that might never be called. Because once we have clarity about what type t is, we compile all the statements here. And that means if you pass, for example, an int, the else part with the pushback still must be valid, although it will be never called. That's the rule of templates. Instantiate all or nothing of a function template. So what could we do with that, or what have we done with that in C++17? We introduced a compile time if. It's called if const expert. That's a way to say at compile time, let's decide whether we take the first or the second part of this if statements, so whether we discard the part that is not true or not chosen according to the condition that is passed. And that's code that's okay. It's in C++17. So you no longer need nasty tricks here to decide what part to call, which means in practice in the past you had to overload different functions. So now we can have one function, and inside the function we can conditionally compile one or the other thing depending on compile time checks. This can be written a little bit easier. Look at the is arithmetic colon value. If you're a little bit hating typing the colon or whatsoever, we have a new is arithmetic v, which is a shortcut for the thing just added before. So, assume we want to do this on a vector, but the vector should be locked because we have concurrent code here. So let's think we enlarge this by having a lock guard. So before we insert all the values to the vector, we lock a value mutex. So a mutex granting exclusive access to the vector. That's fine so far, unless, first of all, another feature here. What drives people a lot mad in the past here is that the lock guard needs the type of the mutex once again. That's no longer necessary. As for functions, template parameter types can be deduced when you use class templates. So you can skip the angle brackets with the std mutex type. The type std mutex is derived from the past object which is an std mutex. And if you now but want to change that and want to say, well, we should not lock this vector if the function does other things than just push backing some new values, we might move the whole thing into the function, which means we need another argument beside the collection, a mutex, and inside the function, before we call pushback, one way or the other, we lock the passed guard. Okay? So let's look at this statement. We have a lock guard, and we have an if const expr here. Can we make this a little bit easier? Yes, we can, because we not only have a switch with initialization, we now also have an if with initialization. And that's also true for if const expr, for the compile time if. So here you see 3 different new C++17 features in a row, which is compile time if, then an initialization, where you don't have to specify the template parameter type, it's deduced, and then the condition. Okay, and because this lock guard is valid until the end of the if, we no longer need braces around this, because at the end of the else part, this lock of the mutex will be removed. Can we improve that even better? Well, we could say the caller can give us an arbitrary number of mutexes for whatever reason. You see how this is done by saying I have a variadic template here on the top there, and we can internally use a new type we introduced, which is called scoped lock. Scoped lock locks a couple of mutexes passed, so that the caller can, for whatever reason, say, when I call insert, I pass you 2 or 1 or none or 3 different mutexes, and they are all locked. And the good thing is, we're using here a function we already have in C++11, which guarantees that we have a deadlock avoidance mechanism here. So the order of the locks is not guaranteed. It will find out what is the right order not to have introduced here a deadlock. Good. So everything is fine here? Well, one problem we have, or might have, look at the definition in yellow in the middle. The scoped lock, LG, taking as an initialization the past mutexes. You might fall into the trap to say, I don't need LG here, the name, so let's skip it. That's unfortunately not so good, because now in the initialization you create a temporary lock or multiple locks that end their life after the initialization, not at the end of the if, after the initialization. So before the rest of the if statement is computed and processed. So please don't do that. This is a fatal runtime error. It will compile. Nobody will recognize this until your vector is totally screwed up. So don't do that. Good. Class template argument deduction. Let's go through a couple of other examples here. We have here vector, all the vector constructors with class template argument deduction. So by deducing argument types without passing them to a class, we can now also initialize an std vector v1 by 2int. The int is deduced, or by one int. It's deduced because the last constructor initializer list of t deduces because we pass ints t to be int. If we use parentheses here, then the last constructor cannot work. So this will deduce that we take the constructor, I think it's a fourth constructor over there, here, taking a size and a t passed by reference. So therefore we know what a t is. But if we just pass the 8 without a value, then this constructor would be called, this constructor does not deduce t, so this will not compile. So then you have to specify what t is, so you can't skip the angel brackets with the vector. And if you pass 8 empty strings, what happens then? Does this compile? Who thinks this compiles? Who thinks this doesn't compile? Who's awakened in this room? Oh my goodness. Who is not awakened in this room? Who has no hands? Okay, good. Well, the funny thing of this is it deduces the element type. It works. It deduces the element type to be of the type which we pass. What is the type of an empty string? Const char pointer? Wrong. It's an array of one constant character. It's not the same. It's an array of one constant character. And that's important because here the argument is passed by reference. And if it's passed by reference, by rule, template parameters do not decay. So it deduces t to be an array of one constant character. And that works. It is as if you would have declared vector of array of one constant character. The problem is this does not compile then, because inside in the vector code it's not allowed to have this t type. So that's the rule, that's the reason this does not work. And finally, let's look at another thing. Let's take a set of strings and use this set of strings to initialize a vector with all the elements of the set of strings. Well, is this correct? Well, we pass the begin and the end. Assume we fill the set of strings by something. We pass all the elements to v6. This might look like that, but it isn't, because the last constructor is called. So the deduce type is a vector of set of string iterators. Remember, brace initialization always takes elements. So this is a vector of iterators. You can here use not the braces, parentheses, and does this work? No, because we can't deduce the element type. There's no constructor where we can deduce t from. And because we can't deduce the element type here, we introduce something in the standard. This is in the standard. It's a so-called deduction guide. And this is a guide where we can say, in case my constructors are not enough to help you to find out what is type t, I can tell you how to find out what is type t. And we say here, if we get two iterators, then let's use the type of the values the iterator refers to as the value type of my vector. And by that, the first thing still is a vector of iterators. But the second thing, now using parentheses, deduces that this is a vector of string and will be initialized by all the elements from the set. You like this? Well, I said you. Cool new features, cool new traps. This, by the way, is a full deduction guide, fully specified. There's another little caveat I want to show you. If you have a vector of two string literals in curly braces, does this compile? Yes, it does, because in an initializer list, the elements decay. They have different types, but they decay to the same type, const char here. So this works. This initializes a vector of string literals of different size. How about using parentheses here? Which constructor is called? Oops, that was the wrong button. The constructor that is called is the one here, taking two iterators. Because the iterators here are passed by value, they decay also to const character star, and that means that we initialize the vector by all string literals between the location of high and the location of word, which is a cordump at its best. Otherwise, you get really, really crazy behavior. So beware. Okay, let's talk a little bit about more variadic power. Who has seen variadic templates before? Okay, here's the example. Print takes one argument and an arbitrary number additional arguments. So let's, for example, pass 3 arguments. This will be expanded to call print for the first argument being const character star. Why const character star? Because we pass the first argument by value, so it decays to the corresponding pointer type. And then we call for the remaining arguments print again. And this recursively instantiates print again, where the first argument is a double and the rest is just a string. And then this instantiates again a print for an std string. And when this is used, then the string is written out, and we call print for the remaining argument after the first argument. There is no other argument. So this calls print, the empty print, and the empty print is the end of the recursion. That's C++ 11 code. That's nothing from C++ 17. But we have to talk about that. First of all, there's a size of ... operator introduced in C++ 11. So smart people try to program the whole thing as follows. They say, if the number of remaining arguments is greater than 0, then I call print with the remaining arguments. Does this compile? Hey, you know the answer now. No, because compile time and runtime issues. The template is instantiated as a whole. So even if you pass only one argument, or finally have only one argument, so even if the remaining arguments is 0, still the print call will be done for the remaining arguments, and if it is not defined, it will not compile. However, we have now if const expr, so this will compile now. There's one problem we have with that, which is the general technique used here is to say, let's pass an arbitrary number of elements and then process one after the other. And that means at compile time, we instantiate this template again and again and again and again until we process all the parameters, which takes compile time. So we introduced something new in C++ 17, which is called fold expression. If you want to apply the same operation to all of your variadic number of arguments, then you can use a fold expression. And that's this strange thing here in red. In parentheses, 3 dots, an operator, and your variadic template parameter, which we call a parameter pack. And for example, this way you can say, I pass 2 ints, and this expands to 7 plus 4. If I later on pass 3 ints, I 1000 and I again, this is expanded to I plus 1000 plus I. So an arbitrary number of elements will be expanded, and the operation here in this parenthesis will be called. This is exactly the syntax. It has to be written that way. And you can also pass, try to pass other types. For example, string littles will start not work because plus for string littles is not possible. But if you pass an std string, then it is possible because an std string plus high compiles, and then the result is an std string, which we can also use to add another high, and this will compile. Okay, I skip a couple of things here. So we use that, for example, in a new thing for std array. So std array is this type where we not only have an element type, we also have the number of elements there. So you don't have to specify, again, type and number. So this will be deduced std array of 9 int. How does this work? Because we have in the standard something like this. We say there's a deduction guide. If an array takes 1 argument of type t and an arbitrary number of additional argument of any type, then we deduce that the array is an array of t, and the second argument, the 9, is 1 plus the number of the remaining arguments. So therefore this works. However, we don't want to have here the problem that these elements to initialize have different types. So if we suddenly have a double here, this should not compile. So how did we do that? Well, we expanded the deduction guide a little bit by this. This says this whole deduction guide, which is a template, should only be enabled, so visible for the compiler, if type t and each of the other types have the same type. And this is a fold expression that expands the AND operation for is same v for t and any other u that is passed here. Okay? So why did we come to here? Because we wanted to print all the elements, and we had to use a recursive approach in C++11 for that. Now, what can we do in C++17 with that? Well, we can write it that way. That's all. You can, in addition to this fold expression, also have an initial value. So let's write out to standard out all the elements with the output operator. So, which means that this whole expression prints all the elements. Any number of arguments you pass here will be printed right behind, and this will not work by recursively instantiate the template, which takes a lot of time. The compiler will at compile time expand this iteratively to the corresponding code. The only problem you see is we have no space in between. How can we deal with that? Well, we can't expand this statement. This has to be the syntax of the statement, but parts of the statements can be expressions. So let's convert this as follows. Let's print out to cout all the elements with a space before. Well, we make it better. The first element is special. We just print it so that we only have a space between elements. So for all remaining arguments, we print out all these arguments with a space before, and space before is a helper function printing out a space and returning then the argument. Which essentially means we compile something like this when the template work is done. Initialize the string and high, and then print out high, and then space before 7.5, space before string. If you read this code, this here, we needed another fix in the language to make this valid code. this code has a problem. Before C++17, this code might not have worked. And here, really, it depends. So what was the problem here? Sequence point, yeah, the order of evaluation. It could output high space 7.5 space world, or it could output high space 7.5 world. Because it was not guaranteed that space before of both expression would be called before we start with the actual output. So the compiler could compile this to first call space before for both arguments and then take the result of the argument to print it out later. This was fixed in C++17. We have introduced new guaranteed evaluation for order for a couple of operands. For example, the output operand, because this is one of the biggest problems we saw in practice. And so this will guarantee to work and to print now high 7.5 world. But beware, we don't have guaranteed evaluation order from left to right everywhere. For example, if you pass arguments to a function, still the evaluation order is undefined. So if you pass this to a print function, taking all the arguments, it might again happen that these two space before statements are called before the arguments are used in the function. Okay? So, can we improve this a little bit? Yes, we can. Look at this. If we don't want to have a function outside, let's use a lambda. And let's, just instead of using space before, let's take the argument and print the argument with a space before. And what is used here? This is the comma operator. You can use this fold expression with the comma operator, which means call this lambda for all the arguments, comma separated in one statement. So we have an easy way now to apply a function call to each and every variadic argument we have now in template code. Of course, it's a good idea to make a parameter out of the separator. So with the default argument that the separator is a space, so we can now say print of these arguments prints a space between, but print with a single character prints a dash in between, or the character we pass. Can we also pass here a string? Yes, we can make that because we have a new feature. Look at this here on top. We can write here auto. And auto in the template means any valid template parameter type this can become. So we can now write, let's print by default a character space. We can print pass as a separator between the arguments a single dash, or we can create a static constant string and we can pass this string. By rule, this can't be passed directly here. You need this line before. This will probably be fixed in C++20. Good. Okay. Other example. Let's look at the time. Who learned something already? Who's totally confused? Yeah. This is a typical crowd of C++ programmers. Totally different example. Let's initialize a vector of strings and let's place some strings in this vector so that we get the following sequence: lowercase id and then a numeric value, then capital ID and then the same numeric value, and we make this in a loop with all the numeric values we pass. So you get a sequence of these values here on the right. Okay, let's sort them. This is sort. Let's sort them from begin to end, which would sort according to the ASCII code. The interesting part is not what is the output. The interesting part is how long does it take. And we can also sort substrings. So just ignoring the first two characters, which would mean we sort according to just the characters of this numeric value. And here you see the numbers. If we call sort For 100,000 elements, we need something like 25 something, 22 something. This is, I think, milliseconds on my laptop, but that's not portable, this number. But you get an idea that taking the substring is significant longer. Why that? Because substring creates a new temporary string. And then we use this to compare. Can we do this better? Yes. Let's convert the string into a string view. This is not a string, this is a view to the characters of a string, or to a characters that are hold somewhere in your program. And by doing that, look at the numbers. You are even better than the normal sort here. What's happening here? String view is a new type. So the idea is, if you have some character sequence in your program, like for example a string literal, you can pass it to a string, but if you pass it to a string, the string has to allocate memory unless it has a short string optimization and the string is short. That means it creates a copy of the value. And if you instead create a string view, you just view to the original character. So you have a very, very cheap object, which we normally pass only by value, and just about the pointer to the beginning of the sequence and the number of characters there. So it's something like a string-like API for a pointer to a character sequence. And by the way, it's as dangerous as that. So there are conversions, so we can use at any time a string as a string view. You have seen that in the example. And that means we have here a string view to the string, which is fine as long as the string is there. Beware that you have a problem when this string is no longer there. So we have introduced a dangerous data type. Yeah? If you in future read something with underscore view, alarm bells must ring in your head. As for pointers and references, this creates more danger than references. So I give you one example where this creates danger. This is a string view, initialized by string literal. And now let's introduce an operator plus. Somebody has written an operator plus for two string views. So plus is not supported for string views, but we can convert them to strings, call plus, and then of course we create a string, not a string view, because we create a new temporary string with its own memory, and we have to return that. So assume you have written this function. Somebody has written this function in your code base. And another clever guy in your team has written a very clever template. The template is this. This looks pretty okay, but it isn't. It takes two arguments of type t, calls plus, and returns them as t. The assumption is int plus int is int, string plus string is string, but string view plus string view we have just defined differently. So what happens if we call this sum for passing twice our string view is we create inside this function a temporary object, which is an std string. We return this, but the return statement says, or the template says, the arguments have type string view, so the return value has type string view. So we convert this to a string view, which refers to the characters in the string. But they are temporary object, local in the function, so at the end of this function, this temporary object is gone, and we return the string view. Bingo. Runtime error, not be warned, you are not warned by this by the compiler. You will just run into this problem. So be careful. Who has made something wrong in this code base? Yeah? The one who wrote the operator? I don't think so. The operator is safe. None of them? I don't think so. It's a return type of sum that is a problem. The guy who wrote this template made a mistake. You should know, if you write templates, that auto is your friend. So return type auto is a problem unless you return it in templates. And even if inside you have a type T, return it with use auto there. So use auto here, please. That's important. So with that knowledge, let's go back to our example and make it even faster. How can we do that? We can use the parallel STL features we have. So there's a new first argument in the algorithm, and we can pass here saying this should run as usual sequentially, but we can also say this should run in parallel using multiple threads. So, what is the difference? Look at the numbers. This is not a proof that the numbers depend on your platform, but it demonstrates that you can get a big performance win by switching to parallel algorithms. This was done by my laptop, which is just a four-core Intel 7 something laptop. So it's an ordinary laptop. And we get impressive numbers by switching to parallel execution here. So one last thing about C++17 talking about parallel algorithms, because I told you and promised you we need caveats, or we have caveats. Or you have to beware about caveats? No, what's the English word? Doesn't matter. Here's another example. This is accumulate. Accumulate accumulates all the values in a sequence in a passed range. So assume you have 10 times the sequence 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 10 times. And here you want to accumulate the values, and you don't accumulate them with the usual plus. You accumulate them with something called squared sum. This is a lambda, which I define as follows. It says, take the values I have so far and add the square of the next value. So the effect should be that I, for example, if my first elements are 1, 2, 3, 4, I call 0 plus 1 squared, 2 squared, plus 3 squared, plus 4 squared, which, by the way, is always 30. So these all values squared is 30. Good. Let's call accumulate. And surprisingly, the number is, because we have 10 times the sequence of 1, 2, 3, 4, we have an output of 300. Good. Can we call this in parallel? No, there is no accumulate that takes an argument, run this in parallel. There is a different algorithm. Why is there a different algorithm? The algorithm is called reduce, and we can call reduce saying run this in parallel with multiple threads, and we create the same output. That's fine. Okay. Let's extend this example a little bit, and let's switch from 10 sequences of 1, 2, 3, 4 to 1,000 sequences of 1, 2, 3, 4. Surprisingly, the output of both algorithms is 30,000. Let's extend this a little bit more and switch to 1 million elements and call accumulate and reduce. And suddenly, with the parallel algorithm, we get a totally confusing result. What has happened here? The problem is, it was not okay to pass this to the parallel algorithm because reduce requires that this is a commutative operation, and this is not a commutative operation. Think about what a parallel algorithm should do. They could go here and say, I first compute 1 plus 2 square, and later on, whatever I have on the left, then the thing on the left plus the thing on the right squared, which means that the same elements are squared multiple times. What is surprising is that you see this problem with 1 million elements, but we didn't see this problem with 10,000 elements. And that's important to know. The parallel algorithms are defined in a way that they don't have to run in parallel. It's about the implementation provider, the vendor, when parallelization is used. And some implementations only use parallelization with a certain amount, a number of elements. So your test cases should be big, not small. And by the way, to solve this, we have a new algorithm for that. That's transform reduce. Transform reduce is separates the two things here. So because this is not commutative, we say for each element we compute the square. That's one lambda argument. And then we add the result. That's another argument. And then internally multiple threads are used to compute the result. And everything is fine and about twice as fast. Is that all? Well, one nice little thing here. Look at this. Plus, parentheses for initialization? No, use curly braces. And surprisingly, you don't need the angel brackets anymore because this is another example of class template argument deduction. That's it. These are my examples. So I have to switch a little bit. I don't have time to show you all examples. So let's summarize. I didn't show you all examples, but you saw a couple of things. And the interesting thing is, whatever we introduce here in this C++17 creates a lot of minor steps. But combining them is an interesting feature. And by combining them, you might also run into traps. And you should be aware of that. Some books already cover C++17. Our C++ template book covers C++17 already. And I have written a C++ book, an ebook, which is available already, although it's not fully done yet. This is an experiment, so you can get it, and you get all the updates for free, and you get it for a pretty cheap price. And as an advertisement at the end of this talk, I just offered a special offer for this book. If you order it in this week with this special website, you get it for a very special minimum price. There's a recommended price and a minimum price. For those who have a company that pays the book, please pay the full price. Because I do this for a living. Okay, I hope you learned a couple of things. You learned that there are new things. I didn't cover all. There's more to tell. And maybe next time I give you some more examples. Thank you very much for your attention.
Thank you, Nico. So are you up for taking one or two questions?
I'm here.
One or two questions?
Yeah, it's more about C++20, mainly regarding the ranges that will be added in C++20, and if whether or not they will have parallel STL support.
Does ranges have parallel STL support? I don't know. My problem is I follow a little bit I follow a lot what we standardize now, but my book still is not done covering all the features of C++17. It only has 400 pages, probably 50 are left. And I usually check about all the details once we go to C++20. C++20 will be a lot bigger than C++17. A lot of new features will come, and then the combination of these features is interesting. You're right. I'm unfortunately not able to answer your question now.